May 19th, 1940, Pas-de-Calais, France. Oberstleutnant Hans-Werner Lerche stood in a muddy field staring at the Spitfire that had belly landed 3 hours earlier. The British pilot was already in German custody, unhurt, defiant. But Lerche wasn't interested in the pilot. He was interested in what sat beneath that elegant fuselage, a 27-litre Rolls-Royce Merlin engine. Still warm, still intact, the most advanced production aircraft engine in Europe, and now, for the first time, Germany had one they could take apart. Lerche was Rechlin Test Center's chief test pilot. For 2 years, he'd been flying captured enemy aircraft, dissecting their capabilities, reporting their weaknesses back to Berlin. He'd flown French fighters, Polish bombers, even a Soviet I-16 that forced-landed near Minsk. But this was different. The Spitfire represented British engineering at its peak, and the Merlin represented something German engineers didn't want to admit, that despite all their technical sophistication, despite the Daimler-Benz 601 engine that powered the Messerschmitt 109, the British had built something better. The Luftwaffe technical officer arrived at 0800 with a team of engineers from Daimler-Benz. They photographed the Spitfire from every angle, measured its dimensions, documented every panel line, every rivet, every control surface. Then they began the careful process of removing the Merlin, disconnecting fuel lines, hydraulic connections, the engine mounts. By 1400 hours they had it free, 1,100 pounds of liquid-cooled V12 engineering, crated and ready for transport to the Daimler-Benz facility in Stuttgart. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Spitfire was one of hundreds of Allied aircraft that would fall into German hands during the war. But this particular capture came at a critical moment. The Battle of France was ending. The British Expeditionary Force was evacuating at Dunkirk, and Hitler was already planning Operation Sea Lion, the invasion of Britain. German intelligence knew the Royal Air Force would be outnumbered, but they also knew the RAF had 2 fighter aircraft that had performed far better than expected. The Hawker Hurricane and the Supermarine Spitfire, both powered by the Merlin. The Daimler-Benz 601 engine had been Germany's pride. Developed from 1933 through 1936, it represented German engineering at its finest, a 33.9-litre inverted V12 with direct fuel injection. The fuel injection system was particularly sophisticated. It allowed Messerschmitt pilots to dive away from pursuing Spitfires by pushing -G, something the carbureted Merlin couldn't do without cutting out. The 601 produced 1,300 horsepower at altitude. It powered the 109, the 110, the Heinkel 111. It was the backbone of the Luftwaffe's fighter force. But German engineers had noticed something troubling during combat over France. The Spitfire could outclimb the 109 at certain altitudes. It could sustain higher speeds at 30,000 feet. And pilots returning from engagements reported that British fighters seemed to have more power available when they needed it most. The -G advantage was useful. But if the Spitfire pilot could simply outclimb you to begin with, the dive escape became irrelevant. The captured Merlin arrived at Stuttgart on May 22nd, 1940. A dozen engineers gathered around the shipping crate like surgeons preparing for a complex operation. The team leader was Rolf Schwabe, 38 years old, chief of advanced engine development at Daimler-Benz. Schwabe had designed much of the 601's supercharger system. He understood how to extract maximum power from internal combustion engines at altitude. He'd studied British engine development through technical journals before the war. He knew Rolls-Royce's reputation for quality. But he also believed German engineering was fundamentally superior, more scientific, more rigorous, more advanced. That belief was about to be tested. The disassembly began methodically. External components first. The coolant system with its vulnerable forward-mounted header tank. The carburetor with its infamous -G weakness. The exhaust manifolds. The accessories. Each part was photographed, weighed, measured. Schwabe's team documented everything. Then they moved to the crankcase, removed the cylinder heads, examined the valve train. the supercharger, the crankshaft, the connecting rods, the pistons. What they found didn't match their expectations. The Merlin was smaller than the 601, 27 litres versus 34 litres. German engineering philosophy emphasized displacement. Larger engines meant more torque, better reliability, longer service life between overhauls. The Merlin's smaller size should have meant less power. But combat reports clearly indicated the Spitfire performed as well or better than the 109 at most altitudes. How was a smaller engine producing comparable or superior performance? The answer was in the details. Schwab examined the supercharger first. The Merlin used a single-stage two-speed mechanical supercharger with a barometrically controlled fluid coupling, not revolutionary. German engines used similar systems, but the impeller design was different. The inlet geometry, the diffuser angles. Someone at Rolls-Royce had done extremely sophisticated fluid dynamics calculations to optimize airflow at high speeds. The result was a supercharger that maintained efficiency across a broader altitude range than comparable German designs. Then there was the metallurgy. The connecting rods were forged from a steel alloy that Schwab's team couldn't immediately identify. Light, strong, precisely machined. They measured the tolerances on the bearing surfaces. 3/10,000ths of an inch, tighter than standard German practice for production engines. This wasn't prototype quality precision. This was series production. Rolls-Royce was manufacturing engines with tolerances that Daimler-Benz reserved for racing engines or limited production runs. The crankshaft showed similar quality. Nitrided surface hardening for wear resistance, precision balanced to minimize vibration. The journal surfaces polished to a mirror finish. Every detail suggested a manufacturing capability that exceeded what German industry was achieving in volume production. But the real surprise came when they examined the individual components under magnification. The machining quality was extraordinary. Tool marks were minimal, surface finishes were consistent, thread quality was precise. This engine had been built to standards that required not just good design, but exceptional manufacturing capability. Machine tools, skilled operators, quality control systems that caught defects before assembly. Schwab called a meeting with his senior engineers on May 28th. They gathered in the Stuttgart facilities conference room. Outside, the spring weather was perfect. Inside, the mood was subdued. Schwab presented his preliminary findings. The Merlin represented a significant achievement in aircraft engine design. More importantly, it represented a manufacturing capability that Germany needed to understand. One of the younger engineers raised the obvious question. If the Merlin was this good, why did it have the negative G weakness? Why use a carburetor instead of fuel injection? Schwab's answer was careful. The carburetor was simpler, fewer parts, easier to manufacture, less prone to failure. Fuel injection provided tactical advantages in combat, yes, but it also added complexity, weight, potential failure points. Rolls-Royce had made a calculated trade-off. Sacrifice some combat capability for reliability and ease of production. And they'd recently heard intelligence reports that British engineers had developed a simple device, a restrictor plate, that largely solved the negative G problem. The British weren't standing still. The meeting concluded with Schwab's recommendation. Germany needed to accelerate development of the 605, the next-generation Daimler-Benz engine. But more fundamentally, German industry needed to examine its manufacturing processes. The Merlin demonstrated that the British could produce advanced engines in quantity with precision that matched or exceeded German capabilities. That suggested industrial resources and organizational systems that Germany had underestimated. June 1940. The Battle of Britain was 3 weeks away. Schwab's detailed technical report on the Merlin landed on the desk of Ernst Udet, Director General of Equipment for the Luftwaffe. 58 pages, technical drawings, metallurgical analysis, performance calculations, and a conclusion that contradicted everything German military doctrine assumed about British industrial capability. Udet read the executive summary twice, then called his chief technical advisor. These numbers can't be correct. 27 litres, producing 1310 horsepower at altitude. With production tolerances this tight, across how many units? The answer shocked him. Intelligence estimates suggested Rolls-Royce and its shadow factories were producing 1,500 Merlins per month, not prototype engines, not limited production runs, full-scale series production, with quality control that ensured every engine met specifications tight enough to make German engineers nervous. The implications were strategic. Britain wasn't just defending itself with a handful of excellent aircraft. Britain had the industrial capacity to replace losses faster than Germany could inflict them. And the engines powering those aircraft were, in several critical aspects, more advanced than anything Germany was producing at similar scale. Udet ordered additional analysis. He wanted to know exactly how Rolls-Royce was achieving these manufacturing tolerances in volume production. Where were they getting their machine tools? What manufacturing processes were they using? How were they training workers to maintain such precise standards? The intelligence reports that came back painted a picture German planners found difficult to accept. Rolls-Royce had established shadow factories, massive production facilities built specifically for wartime engine production. Ford's Trafford Park plant, dedicated Rolls-Royce facilities in Crewe and Glasgow. Each factory employed thousands of workers, many of them women with no previous engineering experience. And they were producing engines that met specifications requiring precision normally associated with master craftsmen. The key was standardization. Rolls-Royce had redesigned the Merlin for mass production without sacrificing quality. They'd developed gauges and fixtures that allowed semi-skilled workers to machine parts to precise specifications. They'd implemented statistical quality control, catching defects early in production before they propagated through the assembly process. They'd created training programs that could take someone with no mechanical experience and turn them into a competent engine assembler in weeks. German industry hadn't done this. German aircraft engine production still relied heavily on skilled craftsmen, master machinists, fitters who hand-fit components during assembly. It produced excellent engines, but it couldn't scale. When demand increased, German factories couldn't simply hire more workers. They needed to train more master craftsmen, and that took years. The Merlin examination team discovered something else that troubled them. The engine used over 14,000 individual parts: pistons, valves, bearings, fasteners, seals, gaskets, thousands of small components, each machined to precise specifications, each available as spare parts for field maintenance. The supply chain logistics required to keep that system functioning at scale implied organizational capability that exceeded anything Germany had achieved in aircraft engine production. But the most significant finding was in the supercharger design. Schwabe's team reverse-engineered the impeller geometry and ran fluid dynamics calculations. The Rolls-Royce engineers had optimized the blade angles and diffuser design using principles that were about 10 years ahead of where Daimler-Benz was in their own development programs. This wasn't just good engineering. This was advanced scientific understanding applied to production engines. How had Britain achieved this? The answer, they gradually pieced together, lay in research programs that predated the war. Rolls-Royce had invested heavily in supercharger development for racing engines. The Schneider Trophy competitions of the 1920s and 30s, high-speed seaplanes pushing the limits of engine performance at altitude. Rolls-Royce had won those competitions with engines producing 2,000 horsepower. Then they'd taken that racing technology and engineered it for reliability and volume production. The Merlin was essentially a productionized racing engine. Germany had no equivalent research path. The Luftwaffe's focus had been on tactical aircraft for support of ground operations, dive bombers, ground attack aircraft, medium bombers for interdiction. The concept of strategic air superiority through high-altitude fighters wasn't emphasized until the war began. And by then, Britain had a 5-year head start in high-altitude engine development. July 1940, the Battle of Britain began in earnest. Luftwaffe bombers struck RAF airfields and radar installations. German fighters swept ahead, seeking combat with British interceptors. And the pilots returning from those missions confirmed everything the Merlin examination had suggested. The Spitfire was a formidable opponent, fast, maneuverable, and powered by an engine that performed beautifully at the altitudes where combat occurred. Messerschmitt pilots developed tactics to exploit the 109's advantages, dive attacks, using the fuel injection system to maintain power under negative G. Energy fighting that avoided prolonged turning engagements. But these were tactical adaptations to address a strategic reality. The British had better engines, and those engines were being produced in quantities that allowed the RAF to replace combat losses within days. By August, German intelligence was reporting RAF fighter strength remaining constant despite heavy losses. New Spitfires and Hurricanes were entering service as fast as German fighters could shoot them down. The production infrastructure Britain had built around the Merlin was working exactly as designed, and Germany had no answer for it in the short term. Daimler-Benz accelerated development of the 605 engine, larger displacement, higher compression ratio, improved supercharger, but development took time. Testing, reliability validation. The 605 wouldn't reach full production until 1942, and by then, Rolls-Royce would have improved the Merlin again. The two-stage Merlin 61 series, the Merlin 70 for high-altitude operations. British engine development was moving faster than German development could catch up. The strategic implications became clear by September. Operation Sea Lion was postponed indefinitely. The Luftwaffe couldn't achieve air superiority over southern England. British fighters powered by Merlin engines were shooting down German bombers at unsustainable rates, and every analysis led back to the same conclusion. Britain had the industrial capacity to sustain the fight. Germany did not. One German pilot, shot down over Kent in late September and taken prisoner, was interrogated by RAF intelligence officers. They asked him about German views on British aircraft. His answer was telling. "We thought your Spitfires were built by craftsmen in small workshops, a few dozen per month at most. Then we learned you were producing them in factories like automobiles, hundreds per month. We couldn't believe it. How does Britain have this industrial capability?" The RAF officer smiled. "We started planning for this war in 1934. You started in 1939. It wasn't entirely accurate. Germany had been rearming since the mid-30s, but the comment reflected a fundamental truth. Britain had used the years before the war to build not just weapons, but weapons production systems, shadow factories, supply chains, training programs, quality control procedures, the infrastructure needed to fight a long war of industrial attrition. Germany had focused on building a large, modern military force, aircraft, tanks, artillery, an army capable of overwhelming opponents through speed and firepower, blitzkrieg, but blitzkrieg doctrine assumed short wars, campaigns measured in weeks or months. Poland, Denmark, Norway, France, all had fallen quickly. The German military machine was optimized for rapid victory. Britain was fighting a different kind of war, a war of endurance, a war where industrial capacity mattered more than tactical brilliance. And the Merlin engine exemplified that strategy. Not the most powerful engine, not the most advanced in every aspect, but a brilliant balance of performance, reliability, and manufacturability. An engine that could be produced in vast quantities without sacrificing the quality needed for combat effectiveness. The German engineers, who examined that first captured Merlin, understood this immediately. Their report to Udet had been explicit. Britain's advantage wasn't just in engine design. It was in their ability to produce advanced engines at scale, and that capability rested on industrial infrastructure, skilled workforce development, and organizational systems that Germany would need years to replicate. Udet never fully accepted the report's implications. He believed German technical superiority would eventually prevail. Better engines, better aircraft, better tactics. The Luftwaffe just needed time to develop the next generation of fighters and bombers. The Focke-Wulf 190, the Messerschmitt 262 jet, wonder weapons that would restore German air superiority. But time was the one resource Germany didn't have. Every month of the war brought new challenges. The Eastern Front consumed resources at staggering rates. Strategic bombing of German industrial targets disrupted production. Raw materials became scarce. Skilled workers were conscripted into combat units. The industrial base that needed to produce millions of aircraft engines instead struggled to maintain existing production levels, and while Germany's situation deteriorated, Allied production accelerated. America entered the war in December 1941. Packard Motor Company began producing Merlins under license, 55,000 engines before war's end. American production methods refined British designs, tighter tolerances, more consistent quality. Packard engineers even improved some aspects of the Merlin that Rolls-Royce hadn't had time to address during wartime production pressures. The Germans captured more Merlins as the war continued. A Lancaster bomber forced down near the Dutch coast. A Mosquito that belly-landed in Norway. American P-51 Mustangs, powered by Packard-built Merlins, shot down over Germany. Each examination confirmed the original findings. The Merlin represented manufacturing capability that Germany couldn't match, and that capability gap was widening, not closing. December 1943. Daimler-Benz, testing facility, Stuttgart. Oberstingenieur Rolf Schwabe stood in front of a disassembled Merlin 61 engine that had been recovered from a downed American B-17 over Bavaria. 3.5 years had passed since he'd examined that first captured Merlin from France. 3.5 years of war, and the engine sitting on his examination bench proved that Britain hadn't been standing still. The Merlin 61 used a 2-stage supercharger, 2 impellers in series with an intercooler between stages to reduce charge air temperature. The system was complex, heavy, but it solved the fundamental problem of high-altitude performance. At 30,000 feet, where German fighters struggled to maintain power, the Merlin 61 delivered 1,560 horsepower. The Spitfire Mark 9, powered by this engine, could outclimb and outrun virtually every German fighter in service. Schwabe's team had spent 6 weeks reverse engineering the supercharger system. The fluid dynamics were extraordinary. Someone at Rolls-Royce had done computational work that Daimler-Benz engineers estimated would take their own teams another 2 years to replicate. And this wasn't a prototype. This was a production engine. Thousands were being manufactured monthly. In Britain, in America, the industrial scale was staggering. One of Schwabe's engineers, a young man named Werner Holtzmann, asked the question everyone was thinking. How are they doing this? The precision required, the manufacturing tolerances, the quality control. We can barely produce 500 605 engines per month, and each requires extensive hand-fitting. They're producing 5,000 Merlins per month across multiple factories, with tighter tolerances than we achieve. Schwabe's answer was blunt. They industrialized what we kept as a craft. We still think of engine building as an art, master craftsman, individual skill, pride in hand-fitted components. The British and Americans think of it as manufacturing, standardized processes, statistical quality control, workers with 3 weeks of training producing parts that interchange perfectly with parts made in different factories. The implications were sobering. Germany was losing the production war, not because German engineers were less skilled, not because German designs were inferior, but because German industry hadn't made the fundamental transition from craftsmanship to mass production. The same cultural pride in quality and individual skill that made German products world-renowned before the war was now a strategic liability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The 605 engine that was supposed to answer the Merlin had become operational in 1942. 35.7 litres, 1,475 horsepower. It powered the later Messerschmitt 109 variants. Good engine, reliable when properly maintained, but it suffered from bearing problems throughout its service life. The switch from ball bearings to sleeve bearings, combined with increasingly poor quality synthetic lubricants, led to failures that plagued Luftwaffe squadrons. The RLM, the German Air Ministry, officially designated the 605 a sick engine. Emergency power settings were restricted, time between overhauls was reduced, pilots were warned against sustained high-power operations. Meanwhile, the Merlin was getting better. The 66 series optimized for low-altitude performance. The 70 series for high-altitude interception. Each variant represented incremental improvement built on massive production experience. Rolls-Royce was learning from thousands of engines in combat service, identifying failure modes, implementing fixes, feeding improvements back into production within months. German development couldn't maintain that pace. Each engine variant required extensive testing, validation, regulatory approval from the RLM. By the time an improved 605 variant reached production, Rolls-Royce had implemented another generation of Merlin improvements. The development cycle gap was as significant as the production capacity gap. January 1945. The war was in its final months. Germany was surrounded, its cities burning under Allied bombing, its armies retreating on every front. Schwabe was in his office at Stuttgart when the air raid sirens sounded. He grabbed his technical files and headed for the shelter. The files included every report he'd written on captured Allied engines, 7 separate Merlin examinations, 3 examinations of American Allison engines, 2 captured Soviet engines, hundreds of pages of analysis, metallurgical studies, performance calculations. The bombing raid lasted 2 hours. When Schwabe emerged, the testing facility was mostly intact, but fires were burning across Stuttgart. The Daimler-Benz production plant, 3 kilometers away, had taken direct hits. Black smoke rose from collapsed buildings. That plant produced 200 engines per month. Now it would produce nothing until repairs were completed, if repairs were even possible. Schwabe knew the war was lost. He'd known for months the reports from the Eastern Front, the relentless Allied advance through France, the destruction of German cities. But the captured Merlin examinations told a deeper story about why Germany had lost. It wasn't just military defeat. It was industrial defeat, economic defeat, organizational defeat. Germany had entered the war with the world's best-trained army, excellent aircraft, superior tanks in many categories, tactical doctrine that shocked opponents with its effectiveness. But war wasn't just tactics. War was production, logistics, the ability to replace losses, to sustain operations across years of grinding attrition. And in that competition, Germany had been outmatched from the beginning. The Merlin represented everything Germany had failed to achieve. Not because German engineers lacked skill, but because German industry, German culture, German strategic planning had never fully embraced the Industrial Revolution's implications for modern warfare. Mass production required standardization, interchangeable parts, de-skilled labor, processes over craftsmanship. These concepts violated traditional German values about quality and expertise. Britain and America had no such hesitations. Their industrial culture was built on mass production. Ford's assembly lines, General Motors manufacturing systems. These companies had spent decades perfecting techniques for producing complex machines in vast quantities with consistent quality. When war came, they applied those techniques to aircraft engines, tanks, ships, ammunition, everything a modern military required. May 8th, 1945, Germany surrendered unconditionally. The war in Europe was over. American and Soviet forces occupied German territory. Intelligence teams fanned out across the country, cataloging German technology, jet engines, rockets, advanced submarines, night vision equipment, chemical weapons. The Allies were particularly interested in jet technology. German engineers had achieved operational jet fighters years before anyone else. The Messerschmitt 262, the Heinkel 162, revolutionary designs that hinted at aviation's future. But the broader technological assessment revealed a paradox. Germany had achieved breakthroughs in specific areas while falling behind in fundamental industrial capabilities. Yes, Germany had operational jet fighters, but those fighters were unreliable. The Jumo 004 engines lasted 10 to 25 hours before requiring replacement. Why? Because Germany lacked the high-temperature alloys needed for turbine blades. Strategic materials were in short supply: nickel, cobalt, chromium. The elements needed for advanced metallurgy were imported before the war and stockpiled. By 1943, those stockpiles were exhausted. Allied investigators examined German engine production facilities, They found skilled craftsmen working with inadequate tools, precision lathes dating to the 1920s, grinding machines that required constant adjustment, quality control systems that relied on individual inspection rather than statistical methods. The production techniques were 30 years behind what Ford was using in Detroit or Rolls-Royce was using in Derby. One American engineering officer, a former tool and die maker from Michigan, toured the Daimler-Benz plant in Stuttgart after the surrender. His report was blunt. German engine designs are sophisticated, but their production methods are antiquated. They're trying to fight a 20th century war with 19th century manufacturing processes. They hand-fit components that should be interchangeable. They rely on master craftsmen for operations that should be standardized. It's impressive craftsmanship, but it's not scalable. Schwab survived the war. He was interrogated by American technical intelligence officers in June 1945. They asked about German engine development, about the 605's problems, about development programs for advanced engines. Schwab answered honestly. The war was over. There was no point in deception. When they asked what had impressed him most about Allied engines, Schwab didn't hesitate. The Merlin, not because it was the most powerful engine we examined. The American Wright 350 radial produced more horsepower, not because it was the most advanced. We captured a Merlin 24 with a two-stage, two-speed supercharger that was brilliant engineering, yes, but not fundamentally beyond what we could design. What impressed me was the manufacturing capability it represented. He pulled out his technical notebooks, showed them his original examination report from May 1940, pointed to the tolerance measurements, the metallurgical analysis, the production estimates. This engine, sir, he said, represented industrial capability that Germany never possessed. You could manufacture complex machines in vast quantities without sacrificing quality. We couldn't. That's why you won. The American officer, a captain from Wright Field's material laboratory, nodded. But you had jet engines, rockets, technology we didn't have. Schwab smiled sadly. Technology doesn't win wars. Production wins wars. You can design the best weapon in the world, but if you can only build 10 of them, they don't matter. The Merlin wasn't the best engine. It was the best production engine. That's far more valuable. The post-war assessment of German technology confirmed Schwab's analysis. Germany had achieved significant advances in specific high-technology areas, jet propulsion, ballistic missiles, advanced submarines, but these achievements masked fundamental weaknesses in industrial capacity. Germany produced approximately 20,000 jet engines during the war. Britain and America produced over 300,000 Merlins and similar conventional engines. The production ratio told the real story. The Merlin continued in production after the war. Civilian versions powered airliners, derated versions powered tanks. The Rolls-Royce Meteor engine that powered the Centurion tank was essentially a Merlin modified for ground use. 650 horsepower, reliable, easy to maintain. The same engineering principles that made the Merlin successful as an aircraft engine made it successful in other applications. German engineers found employment in Allied countries. Many worked for British and American aircraft companies. Schwab himself consulted for Rolls-Royce in the 1950s, helping develop turboprop engines for commercial aviation. He brought German expertise in high-temperature metallurgy and turbine design. The Allies brought industrial production knowledge. Together, they developed engines that powered the post-war aviation industry's growth. The lessons from the Merlin influenced post-war military doctrine in every Western nation. Industrial capacity became a primary consideration in defense planning, not just weapon design, but production systems, supply chains, worker training programs, quality control infrastructure, the ability to manufacture weapons in quantity without sacrificing quality. These factors were recognized as decisive in modern warfare. The Cold War intensified this focus. The Soviet Union and the United States both emphasized industrial production capacity. Tank factories that could produce thousands of units per year, aircraft plants with automated assembly lines, shipyards capable of launching nuclear submarines on predictable schedules. The competition wasn't just about who had better technology. It was about who could produce more of that technology faster, and cheaper. Schwabe retired in 1968. He'd spent the last 20 years of his career working on engines that bore little resemblance to the Merlin he'd examined in 1940. Turboprops, turbofans, high-bypass engines for commercial jets. The technology had advanced dramatically, but the fundamental principles remained. Good design mattered, but manufacturability mattered more. The best engine was the one you could build in quantity, maintain reliably, and deploy globally. In his retirement, Schwabe occasionally lectured at technical universities. Young engineering students born after the war, studying the history of aviation development, they asked him about German jets, about the technology that was 10 years ahead of the Allies. Schwabe's answer never varied. We had some advanced designs, yes, but we were 10 years behind in the capability that mattered. We never understood that modern war is an industrial process. The Merlin taught me that. A smaller engine than ours, less displacement, supposedly less sophisticated, but it was designed to be manufactured, standardized components, interchangeable parts, production processes that could scale. That was the real innovation, not the supercharger design, impressive as it was, not the metallurgy, excellent as it was. The innovation was thinking about the engine as a product of industrial systems, not individual craftsmanship. He would pause, look at the young faces, staring back at him. Students who'd never known war, who'd grown up in a prosperous Germany rebuilt with American aid and European cooperation. The engine taught us we'd lost before the war even started. We just didn't know it yet. The final Merlin was produced in 1950. Over 160,000 engines total, 32,000 from Rolls-Royce Derby, 26,000 from Crewe, 23,000 from Glasgow, 30,000 from Ford in Manchester, 55,000 from Packard in Detroit, each one built to specifications that ensured interchangeability with engines from other factories, each one capable of sustained operation in the most demanding combat environments, each one representing the triumph of industrial engineering over traditional craftsmanship. Today, dozens of Merlins still fly in restored warbirds. Their distinctive sound, a deep, powerful roar, evokes an era when engine noise was the sound of freedom. When young men climbed into Spitfires and Hurricanes and Mustangs and fought for survival against an enemy that seemed invincible, the Merlin powered them all, not because it was perfect, but because it was producible, reliable, maintainable. The right engine for the war that actually happened, not the war that theorists imagined. The Germans who examined those captured engines understood this eventually. Schwabe's reports gathered dust in archives for decades. Then historians discovered them, read them, realized they contained insights into not just engine technology, but the fundamental nature of modern industrial warfare. The reports confirmed what outcome demonstrated. Wars are won by nations that can sustain production, not by nations with the best prototype, but by nations with the best production systems. The Merlin story became a case study in engineering schools, not for its technical specifications, impressive as they were, but for what it represented about the relationship between design and manufacturing, about the importance of producibility in product development, about the need to think systematically about industrial processes, not just individual components. German engineering never recovered its pre-war reputation for absolute supremacy. Post-war German products were excellent. Mercedes-Benz automobiles, Bosch electrical systems, Siemens industrial equipment, but the mystique was gone. The world had learned that German engineering, for all its sophistication, had failed the ultimate test, war, and it failed not because the designs were inadequate, but because the industrial systems supporting those designs couldn't scale to meet demand. The British and Americans learned the opposite lesson, that democratic, capitalist societies with robust industrial base and flexible production systems could outproduce authoritarian rivals even when starting from positions of apparent weakness. This lesson shaped Cold War strategy. The massive investment in American and British defense industries, the emphasis on standardization and interoperability among NATO forces, the focus on sustainability and logistics as much as firepower and technology. The Merlin's legacy extended beyond military applications. The production techniques developed for wartime engine manufacturing influenced post-war civilian industry, automobile production, consumer electronics, appliances. The methods Rolls-Royce and Packard developed for producing 14,000 parts to precise tolerances became standard practice across manufacturing sectors, statistical quality control, standardized work processes, training programs for semi-skilled workers. These innovations, born from the desperate need to produce aircraft engines in vast quantities, transformed how the developed world manufactured everything. Schwabe died in 1976, aged 74. His obituary in German technical journals mentioned his work on turboprop engines, his consulting for Rolls-Royce, his lectures at Stuttgart University. It didn't mention his examination of captured Allied engines during the war. That work remained obscure, buried in archives, known only to specialists in aviation history. But his reports survived, and they told a story more profound than any official history, the story of an engineer who understood, earlier than most, that Germany had already lost the war when the first Spitfire fell into their hands in May 1940. Not because the Spitfire was invincible, but because the engine that powered it represented industrial capability that Germany would never match, a 27-liter V12 that was, in the most important sense, 10 years ahead, not in design, in manufacturability, in production systems, in the industrial philosophy that treated engines not as works of individual craftsmanship, but as products of reproducible processes. The young Luftwaffe pilots who fought the Battle of Britain never knew this. They died believing German technology would eventually prevail. That better aircraft would arrive. Better engines. Better tactics. The wonder weapons Hitler promised. They didn't understand that no amount of tactical brilliance could overcome strategic industrial weakness. That Britain could afford to lose pilots faster than Germany because Britain could replace both pilots and aircraft faster than Germany could destroy them. The Merlin made that possible, not alone. The entire British war economy, American industrial aid, Commonwealth resources, these all mattered. But the Merlin exemplified the approach that won, building something good enough in vast quantities with systems that ensured consistent quality, not pursuing perfection, pursuing producibility, not asking what the best engine was in absolute terms, asking what the best engine was that could be manufactured by the 100,000. German engineers never fully embraced that philosophy during the war. Cultural factors, industrial structure, educational systems that emphasized individual excellence over standardized processes. All these contributed to Germany's inability to match Allied production, and all these factors were revealed in miniature in that first captured Merlin that Schwabe examined in Stuttgart in May 1940. He knew it then. The evidence was irrefutable. The British had built something Germany couldn't replicate, not in 6 months, not in a year, probably not in 5 years. And the war wouldn't wait 5 years. So Germany would lose, not immediately, not obviously, but inevitably. The Merlin proved it. A smaller engine, less displacement, supposedly inferior to German designs, but superior in the only dimension that ultimately mattered: producibility at scale with consistent quality. That was the lesson. That was what 10 years ahead really meant. Not that the Merlin incorporated technology from the future, but that it incorporated industrial philosophy from a future Germany hadn't yet reached. A future where mass production and standardization weren't compromises with quality, but enablers of it. Where thinking systematically about manufacturing processes was as important as thinking creatively about designs. Where the goal wasn't building the best engine possible, but building the best engine producible. The Germans learned that lesson, but they learned it too late. The war was over. The industrial competition was decided. And the Merlin, still flying in restored aircraft 80 years later, remained testament to a simple truth. In modern warfare, the nation that manufactures wins. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.